Suppose you're in gym class. It was never my best class of the day. And you have to climb up a ladder. And you know two things. First, you know you can reach the bottom rung. And second, if you can reach a rung, you can absolutely reach the next one. So based on this information, can you safely conclude that you can make it all the way to the top, no matter how high the top is? Well, the first assumption says you definitely make it to the bottom rung. Then the second assumption says that if you can make it to the first rung, then you can also make it to the second. And for the same reason, if you make it to the second, you can also make it to the third, and so on. Since there's no upper limit built into our two assumptions, we can keep repeating this loop as many times as we need to get to the top of the ladder. So this idea is the basis for a method of proof called mathematical induction. Mathematical induction works well for theorems that state some property is true for all integers greater than or equal to a certain value. These can be algebraic statements like the sum of all the integers from 1 to n is n times n plus 1 divided by 2. Or geometric statements like every simple polygon has at least one diagonal. In the later case, the integer values would be the number of sides the polygon has. To prove something this way, we have to do two things. First, we have to prove that the statement is true for a specific value. Usually this will be 0 or 1, but it could be any integer depending on the circumstance. This is called the basis step and corresponds to showing that we can make it to the first rung in my ladder example. Now the second step, called the inductive step, involves showing that if the hypothesis is true for k, then it must also be true for k plus 1. Right? This initial assumption that p of k must be true, this is called the inductive hypothesis. And it corresponds to the second assumption in the ladder example, where we assume that if we can make it to rung k, then we can also make it to rung k plus 1. So thinking back to our rules of inference, if I wanted to write mathematical induction as a logical predicate, it would look like this. The premise starts off by saying p of 1, that's the basis step, and for every n, p of n being true implies p of n plus 1 is true. That's the inductive step. And if these are both true, that's the and part, then we have p of n is actually true for every n. So in the upcoming lectures, we're going to spend really most of the rest of this section looking at specific examples of how we can use mathematical induction to prove things from a variety of places. We're going to do some algebraic things. We're going to show some things about inequalities. We're even going to look at a geometric example. But before we do that, there is one other thing we need to talk about. It's going to be brief, but we need to talk about something called the well-ordering principle. And that's what we're going to do in the next lecture.